So here we are, lecture number 4 in a series of 4. So we are at the end of the official July lecture series. Did anybody think that July would go this quickly? It just seems like we started yesterday. But did anybody enjoy what they heard so far? Oh, good. Thank you. Well, I know it wasn't from me that you were applauding. So, Bill, why don't you take it away for the last lecture?
Thank you, Richard. And we can go to the next one. So, I didn't change the date on the, anyway. But this is the right episode. This is tonight's episode. So, in the last 3 installations of the talk, we started out with concepts of geologic time and plate tectonic processes. Then in the next 2 talks, we really dove into what happened. So the history. And we'll conclude with some history tonight as well. We'll continue our journey toward the present. But I wanted to wrap up the series with an emphasis on how we know things. So in addition to telling you what happened, I want to explain how we know it. And so there'll be a little bit of sacrifice in the coverage of the history, which I think other people know better than I do. And we'll try to wrap up with an emphasis on methods. And really, geology is a forensic science. It is an investigative science where you try to figure out who done it. And so we'll try to set this up like the guys in CSI and spend as much time explaining the methods as we do the outcome. So next slide, please. As usual, we want to remember what we know already, and I'll just hit the highlights from last week so you remember what we heard before. Next one, please. So here at the falls, we have the westernmost evidence for a big tectonic train wreck. And you'll remember that there were a series of collisions between North America on the left and a bunch of either volcanic island arc, continental fragments, and Africa itself that culminated about 270 million years ago in a really enormous mountain range being erected just to the east of us. And the local significance of that big train wreck is that all the rocks around here were rumpled up like a carpet that somebody slipped on. So we go to the next one. And so we can use that rumpled up carpet as a model, a mental model, to understand the local geologic map. So all of these colorful stripes here show us exactly the wrinkles in the local rock layers that are like this rumpled carpet. And last time when you came, you all walked home with 4 rocks that represent the actual rocks that are here in the local stratigraphic succession that were all crumpled up. So if we go to the next one, and if we were to take a bulldozer and cut a big trench across those folds and look at it from the side, what we would see is, like the next slide, a series of wrinkled up rocks. So now we're looking at them end on in a cross section. And if you do the next slide, and you'll remember that we got the terminology for these folds, that an anticline is where the limbs of the fold are dipping away from the axis, so that's the anti part. And the other kind is a syncline, where the 2 limbs of the fold are dipping towards the axis, so that's where the syn part comes in. So now, a little bit of new content for this week. I want to show you a model of, a scale model in a sandbox of how something like that forms. So if you click on the play arrow, it should show us a video. So here's some flat-lying layers of rock, just like what the local stratigraphy was like when the rocks were deposited. And now you're seeing the consequences of crashing in with these other continental fragments as they start compressing the local rocks. And you'll see that they deform into shapes that look very similar to what has been documented as the actual structure of the local rocks. So that's a model for how it works. All right, so now let's go on to the next. Now we want to orient those events that we've heard about in the previous 3 lectures back into geologic time context. And you'll remember that if we think about the whole history of the Earth as being like a football field, and if we started out on the goal line, the home goal line, and marched toward the other end zone, that this whole chunk of time called the Precambrian didn't have very much exciting life. And it was this big event right at about the 12-yard line that was the Cambrian explosion, when we had many, many different kinds of multicellular organisms. And so the area from the 12-yard line into the goal line, next slide, that's now represented here, and we can divide it up into 3 chunks: Paleozoic, Mesozoic, and Cenozoic, which is ancient life, middle life, and modern life. So, and where we left it last time is that the red star represents the chunk of geologic time during which the rocks that you can see exposed at the falls were deposited. So from one arm of the star to the other, that's the amount of time during which those rocks accumulated. And just about from the end of the star arm until this big explosion sign, that was all the deformation that happened. So all those different collisions that we saw in the previous slide took place during this amount of time. And it was all done by here, in the Permian 270 million years ago. Next slide. Yeah, so that's what we want to know. What happened? Well, a lot of things happened, but the one that we're particularly going to pay attention to tonight has to do with the Catskills. You know, it's a cat, so we're talking about the Catskills. All right, the first thing that happened was the rocks of the Catskills were deposited. So we started from the end of the arm of that star all through this collisional event. Big mountains kept going up to our east. And just like the Himalayas today, or any big mountain chain you can think of that's actively growing today, it's also actively wearing away. So as the mountains are pushed up, the wind and the water and the rain and the ice and everything else is working hard to tear them down. And the debris from tearing down the mountains are sediments. And those sediments are washed down into the ocean, and they represent the rocks that we can see today in the Catskills. So just like the rocks in the falls were laid down originally flat, and then they got crumpled up by this deformation, the rocks that are exposed today in the Catskills were deposited flat in an ocean out to the west of us. And then the next slide, and they kept getting buried. So the mountains kept going up, the mountains kept being worn away, and more and more and more sediment was deposited in that ocean off to the west. And the rocks that we see today exposed in the Catskills hit rock bottom. They were covered up by as much dirt as they were ever going to get covered by at this point in the middle of the Mesozoic. Actually, it was the Jurassic, if you remember the detailed names. And then the cycle turned around. Pangea started breaking up. The material that was over top of today's Catskills started being lifted up and eroded away. And last event we'll look at is the rocks that we can see on the landscape today stuck their head back out at the surface about 23 million years ago. And that's when their uplift really took off. And now the rest of tonight is going to be about explaining how we know that. How do we know that chronology? Okay, so the next slide, and we should clarify what I mean by the Catskills. So here's a map, Connecticut, Massachusetts, and New York. the Hudson River and all of our familiar towns. There's Kingston, there's Saugerties, there's New Paltz, High Falls is over here. And you can see some of the important bodies of water like the Shokin Reservoir. You guys know the names of these better than I do. But you can catch kind of the local water bodies. The next slide. So when I say the Catskills, I talk about the mountains or the elevations that you can see today inside this white outline. And when you drive up the thruway and you look off to your left, you see the skyline. That's what I'm talking about with the Catskills. Now, we can have a geologic map of that territory. This is made by Chuck Verstraeten. You probably can't read the citation down here, but it'll show up again. And just like the rocks originally laid down at High Falls, these rocks come in an order. They all have different names. The names aren't that important, but we see the youngest ones of them, the top of the pile, is exposed in the southwesternmost part of the Catskills. So this light blue unit, the Honesdale Formation that's at the top of the pile, is there. And as we go to the northeast, we're stepping down through each one of these layers. And so by the time you get to around Kingston Saugerties, that's the bottom of the pile, the Ashokan Platekill and the Mount Marion Formation. And that's where the bluestone, the famous bluestone deposits are in that part of the stratigraphy. But all of this is just a flat-lying pile. It's a layer cake. And the top of the layer cake is here, and the bottom of the layer cake is there. Now, if we were, next slide, if we were to look at one part of that mountain range at Overlook Mountain, next slide, please. So if you stand at Opus 40 and you look up at Overlook Mountain, you can appreciate, you might need to have a geologist eye to understand that geologic map was absolutely showing us flat-lying layers, a layer cake. But if you look up at Overlook Mountain, you can actually see the layers of the cake. And we might need to make it a little darker, but I think you can see that there's some horizontal stripes there. If you would click forward one, I've highlighted the different contacts between the individual layers that you can actually see on Overlook Mountain. And they're very parallel with each other. They are the layers of the cake. All right, so let's go to the next slide. So we want to understand, those are the rocks that we want to understand, the ones that we can see today in the Catskill Mountains. So what are the questions that we could ask about those rocks? And I'll show you the methods that we use to answer them. So the questions are, first, where did the sediments come from to make those layers? Next one is, when did they get there? When did they actually arrive in the basin? After they got buried by all the more layers and layers and layers that came after them, how deep was it? How much dirt did they have over their head? And when was it that they hit rock bottom? And then, once the cycle turned around and they started being lifted up and the overburden was eroded to expose them again, how do we know when they stuck their heads back out? So these are questions that we can answer in a very quantitative, specific way, but you got to do some hard work to get there. Next one, please. So the question, where did the sediments come from? This is a paleogeographic reconstruction of what our part of the world looked like at this point. So we have the Akkadian volcanic arc has been established, and we've got another fragment of Avalonia coming to collide with us. And we have really huge mountains. The crest of this mountain range was about 5,000 meters, so 16,500 feet or bigger at that time. And these were all volcanoes with a shallow ocean to the north in those geographic terms, and a deeper ocean on the other side, where nowadays you can see the Delmarva Peninsula down there. There's Cape Cod, for example. But this was the paleogeographic picture. But this, I mean, this is what the company where I work now, this is what we do. We sell Earth history, and we make maps like this for people who are exploring for stuff. But even though this is a pretty picture, it has to be based on something. We can't just fantasize it in our mind. So we want to say, if I have sediments deposited out here in this ocean, how could I reconstruct what was the material here in the mountains that made those sediments? So next slide, please. Just to bring this to modern day examples, here we've got, that's Malaysia and then all of Indonesia. So Sunda and the Banda Arc, or sorry, Sumatra and the Sunda Arc here. And if we zoom in on those islands, the next slide, and then the next one, so you'll see that we have really dramatically high volcanoes. And that's what we had back in the Middle Devonian right here in our neighborhood. Next one. But yeah, how do we know that? I mean, and this is what I have to deal with every day. Is, you know, somebody's asking me, how do you know that? Well, you got to ask the rocks. They'll tell you if you ask them nicely. And you listen carefully to what they want to tell you. So, if you slice up, and I mean, it's kind of, we do have to bring some extreme interrogation techniques to bear. We slice the rocks into really thin slices. We polish it so that light can pass through it like a sheet of glass, and then you look at it under the microscope. And what would you see? You see sand like that. And there's the job. When I was a graduate student, for example, I looked at hundreds and hundreds of slices like this, and I counted every dang one of those sand grains to know what they were. So what kinds of things would you look for among all those sand grains to tell you what was the source material? Next slide. So the first thing we would look at are heavy minerals. So the majority of what you would see in a handful of sand, most places, is just the mineral quartz. But that's not the only thing that you will find. There are also other kinds of minerals, like apatite, tourmaline, rutile. I mean, they have all kinds of names. But what's useful about them, just seeing that they are there, is knowing that some of these minerals come from very specific kinds of rocks. So a garnet will tell you that it has come from a particular kind of metamorphic rock. Kyanite will tell you that it has come from a particular kind of rock that was previously in a pile of limestone and shale. Zircons, for example, come from very specific kinds of igneous rocks. So immediately, knowing that these specific minerals are there or not, start to tell you the generic types of rock that could have supplied the sediment. Next one. But then if we look at particularly at the zircons are usually zoned. So it is a kind of mineral that grows slowly from magma, and so it has growth rings just like a tree. It has, and what's in the middle of the grain is the oldest, and each successive layer is younger and younger. And because it's crystallizing out of a melt that's evolving, each one of these rings has a little bit different chemical composition. It will have a different age, which we can measure. And this is almost like a fingerprint. So we can, and the parent rock for a specific zircon can be identified by this pattern of age and composition that makes up the rings of the individual zircon. So you count up hundreds and hundreds and hundreds of these zircons, you characterize them, like what kind of families do they come from. You put together the ones that have similar characteristics, and you say, okay, these guys all came from a similar rock body, and now I can go look for that rock body if it might still be left. Sometimes they've been completely obliterated, but at least we know what age they were, and from the chemistry of the zircon, we know something about what the nature of the rock was. And then the most obvious thing are rock fragments. So when those mountains are being busted up into little pieces, sometimes the little piece looks like the original rock. And so you can just pick them right out and say, oh yeah. We were talking about chert earlier. Here's a little bit of a cherty grain. So sometimes the little bits of rocks tell you, they just say, hey, that's me. This is my, you know my parents. already just by looking at me. Okay, so next slide, please. The next question we had posed was, when did the sediments get there? And for that, we use volcanic ash. And if we go to the next slide. So here's the big shout out to Chuck Verstraeten at the State Museum. He knows everything about the Devonian rocks of New York. So we have big volcanoes on the edge of our basin, and whenever they erupt, they make a big ash cloud, and that ash drifts to the west, and it settles out into the ocean, and it makes a rock called bentonite. And all through the stratigraphic pile, we have these thin layers of bentonite. And fortunately, the good thing about them is we can read directly from them how old they are. Next slide, please. So, some of the minerals that are in the ash have potassium in them. Well, actually, a lot of the minerals in there have potassium. And potassium, if you poke it just a little bit, it falls apart, and it makes argon. So and this, you may remember from the very first lecture, that's where a lot of the heat in the earth comes from, is the decay of potassium-40 to argon-40. And so we know from the composition of the minerals in the original rock how much potassium ought to have been there when they started. And so the system is a lot like an hourglass. As the potassium goes away, the argon accumulates. And so you measure the chemistry of the rock, and you look at the ratio between what you started with and what you got now, and the balance tells you how long the clock has been running. Now, very often, the hourglass is leaky. And because argon is a gas, it's a noble gas, it doesn't interact with anything, there's not much to hold it back, it can slip out of the system very easily, which was traditionally a problem, if you back up a minute, was a problem with this kind of dating technique. However, we can exploit the system called argon-argon, because there are two flavors of argon. There's just plain old regular argon, which is 39. It's just there. It's in the background. The amount of it is fixed. Argon-40, we call that radiogenic. It's special argon. It only comes around by the decay of potassium. So if we look at the bottom of this hourglass, if the argon runs away, both the 49 and the 39 are equally good at running away. So we can look at the ratio of them. The more radiogenic there is compared to the plain Jane normal flavor, the longer the clock has been running. So we can use the ratio between the two kinds of argon. Even if not all the argon is there, the ratio between them tells us how long the clock has been running. All right, so that's how we tell the age of the volcanic ash, by using argon-argon or potassium-argon dating, and the ash then tells us the age of the sediments that are right around it. So that's how we know when the sediments got into the basin. Next one, please. Now, how deep did those sediments go? That we're going to figure out using vitrinite reflectance. What the heck is that? Next slide, please. So every rock, every mud that's accumulating in the ocean anywhere is going to have a little bit of organic material in it. And you have in your car, to drive here today, unless you got an electric car, but if you drove here with a gasoline-powered car, that gasoline is the leftover from green slime like that. These small multicellular or unicellular organisms called cyanobacteria are just ubiquitously growing in the ocean. They die, they fall to the bottom, and if they haven't been eaten by somebody else, they accumulate in the mud rocks. And then as the mud rocks get buried and they heat up, that stuff starts getting cooked into what we call organic macerables. And ultimately, if it gets cooked long enough, it becomes liquid, like crude oil, or if it gets cooked even more, it becomes gaseous, it's natural gas. But every mud rock, like your little piece of High Falls shale that you took home last time, should have a little bit of organic material in it. If you were to collect a ton, literally a ton, of High Falls shale from here and crunch it up and analyze it for its organic content, there's probably about an ibuprofen worth, like a few hundred milligrams of organic material in that ton of rock. That's just normal mud rocks. If you start getting a bottle of ibuprofen in that ton, so you have a few grams, then you're talking about a rock that could actually make some oil. But it doesn't matter. As long as you have some organic material, you can start using it for our purposes. Next slide, please. So, as you cook those organic mackerels up, just like if you cook steak or you cook eggs or something, it starts to transform. The proteins and the lipids in the material cook into different stuff. And the useful characteristic for us is that they get shinier and shinier as they cook up. So again, if you make the thin slice of rock, you polish it up, and you bounce light of a very particular wavelength off the particle, and compare how much you hit it with how much bounced back, that's a quantitative measurement. And the more that bounces back, the more cooked up it was, and that means the higher the temperature that it experienced. So next slide. So we can make a chart where we compare the quantitative vitrinite reflectance level to the temperature that has been experienced by the organic material. So we do laboratory experiments to establish that relationship. And then we know that there is a fairly consistent geothermal gradient. As you go down in the earth, it gets about 30 degrees C hotter for every kilometer you go down. Some places it's 27, some places it's 35, it could be even 42 or 19, but most of the time it's about 30 degrees. So you can convert a temperature estimate into a depth estimate. And now some local folks from Syracuse did just that. Next slide, please. They took a whole bunch of samples across New York, and if we go to the eastern New York part where our Catskill Mountains are, next one, please. You see that the vitrinite reflectance of the reflectance of the vitrinite that they separated from the mud rocks in the Catskills is about 2.5 to 3, and that level of shininess corresponds to temperatures of about 200 to 250 degrees C, which is somewhere a little bit more than 5 to a little bit more than 6 kilometers of burial. So those rocks that we see exposed in the Catskills today, we know that at maximum burial, they had about 5 to 6 kilometers, 3 to 3.5 miles of extra material over top of their heads when they were fully buried. And we know that from the shininess of the organic material that's in them. All right, next. And when did that happen? Well, for that, we have to look at fission tracks. So here you're looking at the polished surface of an apatite. It's a phosphate mineral. And you see that it's just been scraped up. It's been blasted. And we can use it. We can exploit that to our advantage. Next slide, please. So the apatite starts out as just a happy crystal. And it's mostly got calcium and phosphate that make it up. However, in the crystal structure, there's a little bit of uranium. It's in the ocean water. It gets incorporated into minerals as they crystallize, or it's in the magma, and it gets caught up in the crystal framework. And as we all know, uranium is unstable. You poke it just a little bit and it falls apart. And those particles that arise when it falls apart, they're like big cannonballs that go shooting off through the crystal structure. And they just rip the snot out of that poor crystal. And the longer that the crystal sits there, the more uranium blows up and the more scars you get in the crystal structure. So you can use this as a clock. The more scarred up it is, the longer it's been. Now, that assumes that the temperature of the crystal is below 60 degrees centigrade. If you make it a little bit hotter, like about 90 degrees, those flaws will start to heal because the mineral gets kind of soft and squishy, and the fission tracks start going away. And if the mineral is above 120 degrees, they can't form at all, because as soon as the uranium blows up and rips apart the crystal structure, It just heals itself immediately if the temperature is that high. So that's the mineral apatite on the A end of the alphabet. There's another mineral called zircon, which we looked at before. It's much tougher. It crystallizes at much higher temperatures. So that range of temperatures, if it's below, for zircon, if it's below 200 degrees C, all the flaws will stay without any modification. If it's 270 degrees, they can't form in the first place because they just heal instantaneously. So for different kinds of minerals, we can use this phenomenon, the fission tracks, as a clock to tell us how long it's been, how long that crystal has been sitting there above a certain or below a certain temperature. So next slide. So there's special software. There's actually a company called Apatite to Zircon, and they have a special software which allows you to, once you have polished up all your hundreds of mineral grains, counted all the tracks, measured how long they were, and used them as a clock, you can use various different minerals and calculate a trajectory. So for this particular sample that the guys from Syracuse took in the Catskills, you can look what temperature did that rock experience over time based on all the different minerals you can measure. And the heavy purple line is the best answer, and then the shaded area around it is the permissible amount of slop. You know, the answer has to lie somewhere in there, and the purple line is the best guess. And whether it's the best guess or the slop, they all hit the maximum temperature after the start of deposition right here at about 175 million years. So now we have actual quantitative measurements to tell us how hot it was, which gives us an estimate of how thick was the pile, and when did it get to that maximum burial. So we were starting to answer most of our questions. Next one, please. The next one is, when did the rocks poke back out? They got to the bottom, and then they started being uplifted, all the overburden was scraped away, and finally, those rocks we see at the surface today started to get back towards the surface. So they started to return to a cool environment. And now we can use a different kind of hourglass that is closed off at cooler temperatures, and it is the decay of uranium to make thorium and helium. And for that, so helium especially is a very slippery character. It can escape really easily. I mean, helium is a tiny little molecule. It doesn't interact with anybody. You can't catch on to it. It always escapes until the rock is really, really frozen. And really, really frozen means at a low temperature like 65 degrees centigrade. So that's getting close to the surface. And it's the same deal. We got the hourglass. We know how much of the parent we started with. We can measure how much of the daughter is left. And we know that the daughter only accumulates when it's cooler than this temperature, so we know that the clock is only running when we're that close to the surface and closer. So next slide. Once again, the same researchers from Syracuse collected some more samples in the Catskills, and here they concentrated on the very shallowest, coolest part of the cooling history, and they can demonstrate using the systematics of these minerals that those rocks really started popping up at about 23 million years. So next slide. So that's the story from the neighborhood, and here we're concentrating on the methods. And I want to give a shout out to all the people who published the information that I could consult to do it. Chuck Verstraeten at the State Museum. He's Mr. Catskills. Anything you want to know about the Devonian of the Catskills and farther west, he's the guy. Lorraine Eglinton is an organic petrologist. She's the one I learned everything I know about that topic from, and that's her livelihood. Is she sits at the microscope and measures the shininess of organic particles so you can figure out how deep the rocks were buried. Dave Gombosi was my colleague at ExxonMobil. He's now in the low carbon solutions part of the company. And he taught me everything I know about thermochronology, that basic concept of fission tracks and uranium, thorium, helium. How do we infer the uplift history or the temperature evolution from the minerals? And then Shalissa Shorten, who is a grad student at Syracuse, and her supervising professor, Paul Fitzgerald, who did the work in the Catskills, collecting hundreds of samples and analyzing them tediously to reconstruct the temperature history that we've just discussed. So what I hope you walk away with now is that all around us, even in our own neighborhood, there are rocks that have a history. And they'll tell us. If we just ask them nicely, they'll tell us what happened, and we can uncover the history. And sometimes we have to work like the CSI guys and get complicated machines and make special measurements, but it's all part of a reasoning process. And any of us who have eyes and brains can engage in this activity and unravel the history around us. And so that's what we did this month. And now I'm done talking, and I'll be happy to take your questions that may come up. Yes, please.